Hello everyone, my name is Pengfei Li, a PhD student from University of California, Riverside. Today I'm going to represent our work, Expert-Calibrated Learning for Online Optimization with Switching Costs. I'd like to thank my co-author Jianyi Yang and our supervisor, Professor Shaolei Ren, both from UCR. Okay, nowadays many real-world problems such as energy scheduling in smart grids, resource management in cloud computing, and load balancing in communication systems can be formulated as online convex optimization, where an agent makes action online based on sequentially revealed information. Here is a real-world example. Suppose we have several users and a data center serving these users. When the user's demand fluctuates, we need to change the server status to match the demand, which minimizes the user's waiting time and energy consumption. As you can see here, maybe when two users left, we may need to turn off one server. Okay, and after a while, maybe 4 users join the pool, and we may also need to turn on 2 servers. Okay, but however, for the 6th server, frequently turning it on and off is not desired, which may increase the total energy consumption and decrease the server's lifespan. Therefore, we also want to minimize the switching costs at the same time. This problem is usually formulated as smooth online convex optimization, or SOCO for short. Here is the mathematical formulation of the SOCO problem. The total cost consists of 2 parts, the heating cost and switching cost. Heating cost is parameterized by YT, and YT is revealed sequentially. Besides, we can assume the heating cost is I'm strongly convex and switching cost is alpha strong convex and beta smooth, which is a common assumption in these problems. Okay, here are the performance metrics of this problem. The average cost measures the expected performance in typical cases, given the environment distribution. On the other hand, the competitive ratio measures the worst case performance. While both empirically and theoretically important, SOCO is extremely challenging. Let's consider a toy example where a robot tries to follow the object. The object's position is revealed sequentially. The heating cost is shown as here. Okay, a simple policy is to minimize the heating cost at each time step. As you can see, the robot runs back and forth, so it pays too much on the switching cost in this case. Therefore, the optimal solution at different time steps are highly dependent on each other. The optimal solution needs the complete offline future information, which is nonetheless lacking in practice. To address these problems, a lot of expert algorithms have been proposed. The state-of-the-art algorithm, ROBD, achieves the competitive ratio here, which already matches the lower bound of competitive ratio in this problem. Though ROBD achieves perfect robustness, the average performance of ROBD is usually inferior compared with modern machine learning models. Machine learning models can achieve much better performance by exploiting historical data available in many practical applications. However, machine learning models are vulnerable to out-of-distribution samples, which means the worst-case performance is not guaranteed here. Actually, the competitive ratio of a CR model is at least here. Okay, I'm an alpha is the problem's parameter, and rho is the prediction error of machine learning model. Okay, and there are some existing work which try to combine the expert with machine learning models. However, the key issue in their method is that they treat machine learning model as a black box and train the machine learning model standalone. In this case, the machine learning model may perform well on its own, but with their algorithm, the already good actions will still be altered. In other words, they are sacrificing a lot of average performance for some robustness. Okay, to address this pain point in our algorithm, we make machine learning model aware of the downstream calibration. We make the machine learning model minimize the total cost yield by the actual action during the training. To achieve this goal, we propose a novel expert algorithm with closed form differentiation, which is non-trivial to design and is vital for gradient-based backpropagation. Besides, we rigorously prove that our algorithm is guaranteed to improve the competitive ratio when machine learning prediction errors are large. In our simulation, we also empirically proved this algorithm can achieve better robustness and better average performance at the same time. Here is the our algorithm. First, we find the minimizer of the hidden cost. Then we use the machine learning model to predict action. Finally, we minimize the weighted sum of hidden costs, switching costs, the gaps towards the hidden cost minimizer, and the gaps towards machine learning model predictions. Then we can get the final action. We need the closed form differentiation of xt with respect to the xt tilde, the machine learning prediction, which will be covered later. The parameter lambda1, lambda2, lambda3 can be adjusted to reflect the confidence on machine learning predictions. Okay, here is the competitive ratio of our algorithm. When optimally set lambda2, the competitive ratio becomes here. We can see the competitive ratio is better than state-of-the-art expert algorithm ROBD when machine learning predictions are good. The second term shows with proper theta, the competitive ratio is better than pure machine learning since the slope is smaller. More details can be found in our theorem 4.2. Here is an intuitive illustration of our algorithm. We can see that when prediction errors are small, our algorithm is guaranteed to improve the performance compared with an expert algorithm, ROBD. For a well-trained machine learning model, this is true in most cases. That's why our algorithm can improve the average performance compared with ROBD. Besides, we can find when prediction error of machine learning model is large, our algorithm can reduce the competitive ratio, which improves the worst case performance. Some of our reviewers challenged us that when prediction error comes to infinity, the competitive ratio of our calibrated algorithm also goes to infinity. Actually, this is a fundamental difficulty of this problem itself. The paper 1 has proven that for any machine learning augmented algorithm, if it achieves better competitive ratio than ROBD when machine learning is good, it can never have a finite competitive ratio when machine learning is arbitrarily bad. Now let's discuss how to train the machine learning model. As we mentioned, all existing works will train the machine learning model standalone with the laws shown here. In this case, machine learning prediction st tilde may work well on its own, but during the inference, some already good actions may still be altered. It's obvious that there's an objective mismatch between training and testing. Okay, so solve this mismatch problem, we can train the machine learning model based on the actual action. However, we can only make sure the post-calibration action is good in this case, but pre-calibration action may not be good since it's not considered here. But the competitive ratio is improved with respect to the pre-calibration actions. So we need good pre-calibration actions. To address this problem, here's our final solution. We train the machine learning model with machine learning prediction error regularization. The weight mu here balance the machine learning prediction error and the average cost in the loss function during the training process. By setting mu equal to 1, we recover the standalone training of pure machine learning model. By setting mu equal to 0, we only consider the post-calibration cost while ignoring the machine learning prediction error. Therefore, we usually set mu between 0 and 1. There are also some technical issues for the ECL2O. First, closed form differentiation of the calibrator is non-trivial. The key idea is to apply KKT condition on line 5 in algorithm 1, which is shown below. Besides, due to the recurrent architecture of the machine learning model, the backpropagation of the calibrator should also be performed recurrently through time. Please refer to section 4.5 of our paper for more details. Next, we'd like to provide a performance analysis for the ECL2O algorithm. First, we show the necessity of training machine learning model in a calibration-aware way in terms of generalization bound of average cost. This generalization bound is lower than training machine learning model standalone. For more details, please refer to our theorem for 5.1. Besides, we show the tail competitive ratio of ECL2O. Here is the row tail. Okay, the hyperparameter mu here in our algorithm balance the machine learning prediction error and the average cost. When mu is between 0 and 1, the tail cost is bounded. In the extreme case, when mu approaches 0, this tail cost ratio becomes very large until infinity. This proof reaffirms the importance of this weighted loss. Okay, and we conduct a case study and perform a simulation on the application of the sustainable data center. Our goal is to facilitate integration of rapidly fluctuating renewables, including wind power and solar power, into a micro power grid serving the data center. The energy reduction request at time step t is related to the weather right now. For instance, wind speed, solar radiation, air density, etc. A snapshot of the trees is shown below. Here is the TSNE visualization of the data. Here we can find for some months, the data distribution is very different between each other. We train on January to March and tested on April to June. That's why on some test samples, prediction error of the machine learning model are large. Here are some baseline algorithms. ROBD is the state-of-the-art expert algorithm, and switch is the state-of-the-art machine learning augmented algorithm, which dynamically switch between pure machine learning and ROBD actions. First, we can find the average performance of machine learning is great, but the worst case performance is not satisfying. Then let's see our expert calibration method. There are some improvements on average performance, and the worst case performance increase a little bit compared with ROBD. But this method sacrifices a lot of the average performance to achieve this robustness, which is the pain point of all existing ML augmented algorithms. Therefore, we propose our ECL2O, which achieves better robustness and better performance at the same time. Okay, and here is the tail cost comparison. We can find our final algorithm ECL2O reduces the cost ratio by a large margin compared with existing methods. Here is the takeaway message. The existing expert calibration methods treat machine learning as a black box model and train it standalone, which may degrade the actual average performance. We propose a new framework to train the machine learning model in a calibration-aware way. To achieve this goal, we propose a new expert algorithm and provide a closed form differentiation of this algorithm. Finally, we empirically show our algorithm achieves better performance and robustness at the same time. And thanks for listening.